Hi, my name is Aaron Dales, and for Lab 6, we were given the initial position of a star and the mass of the star, and from this we had to create a program to find the mass of a black hole near the star based upon how the star moved around the black hole. The results were that the mass of the black hole was 2.136 times 10 to the 31st kilograms. So for this, I created a model using Python for the momentum principle and curving motion in order to find the variables needed to calculate the mass of the black hole. Initially, the star was at the vector 0, 0, 0, and had a mass of 1.989 e to the 30th, given here, and we had a time step of 86,400 seconds, which is equivalent to 1 day. Initially, we had to find the change of x and the change of y variables. So for this, we created x idx plus 1 minus x idx in order to find the change of x, which is used to find the velocity in the x position by delta x divided by the change of time. A similar process was done for the change of y. Then, using these velocities that we calculated up here, we could find the initial velocity and the final velocity. Then, since we found the initial velocity and the final velocity, we could also find the initial momentum and the final momentum by multiplying it by the mass of the star. From here, we were able to calculate the change of momentum over the change of time, because we were able to take the change of momentum and literally divide it by the change of time for one step, which this case was set to 86,400 seconds, like it said over here. That's the time step we were given. So in the model, the 1 day is our time step. Since the force of gravity between the black hole and the star is the only force in this model, the net force is equal to the change of momentum over the change of time. From here, we used formulas derived from the momentum principle that Fnet is equal to Fnet parallel plus Fnet perpendicular. And since we know that Fnet is equal to the change of momentum divided by the change of time, we can say that the change of momentum parallel is equal to the Fnet parallel, and the change of momentum perpendicular is equal to Fnet perpendicular. For simplicity's sake, we found Fnet perpendicular, which is equal to p hat times the magnitude of the final momentum minus the magnitude of the initial momentum divided by the change in time. P hat is equal to the final momentum divided by the magnitude of the final momentum. And then we found Fnet parallel by subtracting the perpendicular force of Fnet from Fnet. All that was put into code and put into this formula here. At the end of this program, we updated the position of the star, and we also created arrows to represent the net force, the parallel net force, and the perpendicular net force, as well as we printed off the values for the mass of the star, the magnitude of Fnet, the vector of Fnet perpendicular, and the vector of Fnet parallel. Here's the model. The black arrow represents Fnet, the blue arrow represents Fnet perpendicular, and the red arrow represents Fnet parallel. Also, that was printed out with the model was an Excel file that gave the position of the star at every point. From there, we were able to take the initial position of the star and input it into this formula I derived here to find the mass of the black hole, represented here by m1. Since gravitational force is the only force acting upon the system, we can say it's equal to the net force. From the model, we were able to find the net force given by this value here, so we're able to say that the gravitational force was equal to the net force, which was about 3.06 times 10 to the 26th. We already knew the mass of the star given to us, which is 1.989 times 10 to the 30th, and we knew the gravitational constant, which is 6.7 times 10 to the negative 11th. We had to find the distance using the values given in the Excel file and the value of the initial position of the black hole, which was given to us here. Using these two values, we were able to find the magnitude of the distance in between and complete the equation. And once the equation was all put together and the algebra was through, the mass of the black hole came out to be 2.136 times 10 to the 31st, which is confirmed by this here. Last but not least, what if, imagine a black hole whose mass you found was replaced by a different black hole but still placed at the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? No, you would not be able to tell the difference because the data would appear the same, and from the data that we gathered, we were able to calculate the mass of the black hole. By changing the mass of the black hole but not changing the data, we would not be able to find the mass of the black hole. Thanks guys, hope you enjoyed the video.